Okay, welcome back. There's a meta topic today, and that is how to simultaneously find the assertion and the proof of a theorem. We'll hit that a couple of times, and it's a nice illustration of this. Well, you can't call it a method, it's something that happens all the time. You know it from calculus, where you have to find the deltas and epsilons as the proof goes, from the way the proof goes. And it applies here as well. So let me start with König's theorem on matchings in a bipartite graph. It tells you one way of phrasing it is to say that either you can find k independent edges in your bipartite graph. Independent means they don't share an end. Or if you can't, you can hit all the edges by k minus 1 vertices. And so you can ask, is that true for non-bipartite graphs as well, for example? Right, so we're talking about the minimum k. So for bipartite graphs, this was one of these nice characterizations like Menger's theorem, or also like the packing covering theorem that we had last time. And in that, both the vertex cover and of all the edges and the maximum set of independent edges would certify each other's optimality in the case that they are both optimal. But maybe if in general the same does not work, and for non-bipartite graphs this does not work. So for example, if you look at a triangle and you consider k equals 2, can you find 2 independent edges? No, you can't. And can you hit all the edges by 2 minus 1 vertices? No, you can't either. Right? So that doesn't work for non-bipartite graphs, but you can ask, well, if you can't hit the edges, if you can't find k independent edges in a non-bipartite graph, can you perhaps hit all the vertices by not k minus 1, but k vertices, or by 5k vertices, or by 2 to the k vertices or something, right? So take your minimum k that you can't find k independent edges in a non-bipartite graph. Can you guarantee that by some function of k many vertices you can hit all the edges? That can be investigated much more generally, not just for covering edges. Think of an edge as a complete subgraph on 2 vertices, but for arbitrary family of subgraphs. And that is the first definition. Let us say that a class of graphs, call it curly H, has the Erdös-Posa property, Erdös and Posa. You know Erdös. Posa was one of his early students. If there's a function, f, little f, such that you can always, in any graph, either find, for any given k disjoint copies of elements of curly H in your graph, in your given graph, call it G. Or else if you can't, then you can hit all the copies of H in your G by at most f of k vertices, right? So either you find k disjoint copies, or you can hit them all, meet them all by a set of vertices that is bounded as by a function of k independently of the graph that you're considering. Okay, so that's the Erdös-Posa property. And why is it called the Erdös-Posa property? Not because Erdős and Posa invented that property of classes of graphs, but because they proved a very particular theorem, namely this theorem for cycles. They proved that the class of cycles has what we might now call the Erdös-Posa property. So here's the theorem. There is a function, little f, such that for all k and g, either there are k disjoint cycles in G, or else, if not, then we can find f of k vertices that meet all the cycles in G. That was the original theorem. It just came out of the blue as one particular theorem, and that's very much Erdős style. So Erdős has this legacy of fantastic problems, and part of the reason why they're so fruitful is that he sort of has this knack for finding the simplest non-trivial case or example of a whole host of problems, of a whole type of problems, where non-trivial does not necessarily mean nearly trivial in Erdős's case. So there are many famous problems still that are unsolved to this day. But the Erdős-Posa theorem is one of this kind. It's a very concrete theorem about cycles, but of course it makes sense to consider it for arbitrary classes of graphs, not just for cycles. Okay, let's concern ourselves with cycles today, and I'll give you a few attempts at a proof, and we'll start with the simplest idea that one can have. You shall see that that will fail. Then we'll make amends and try something slightly different or something complementary to that, and that will fail as well, and then eventually we'll reach a correct proof. So there are no cons this time. I'm not going to show you any false proofs, but I'm going to show you attempts that don't lead to a correct proof, and sometimes one can see that early, but bear with me, and let's develop these together. So we might try to prove this by induction by finding one cycle in a given graph, call it C, and then looking at the rest, G minus C, and ask whether in G minus C maybe we can find K minus 1 disjoint cycles. Okay, so if we can find K minus 1 here, then together with our cycle C, we would have found K cycles and we'd be happy. So K is given at the start, G is also given. This whole graph is G. If not, if we cannot find K minus 1 cycles in G minus C, then by induction, we can hope to find some set of vertices in G minus C that cover all the cycles there, and not too many. At most, f of K minus 1. Many vertices here. And we'd like that to be a good outcome as well in the induction proof by being able to say, oh, well, if we can cover all those cycles in here by f of K minus 1 vertices, well, we just have to cover C as well. So add a vertex and we're done. So we can let f of k be f of k minus 1 plus 1, and you can guess what f might be if we can do that. So is that a correct? Well, this was a false proof, so where's the error here? Well, we haven't covered all the cycles in the graph. Right? We've covered all the cycles that live entirely here. We've covered all the cycles that live entirely outside, but we haven't covered all the many cycles that maybe live between the two sides. Okay, so that is not a viable proof strategy, but we might say, okay, well, if we can allow ourselves to add all the vertices of C, then indeed we will have covered all the cycles, right? Because either the cycle lives in here, and then we've covered it by those f of k minus 1 vertices, or it doesn't, and if it doesn't, then it meets C, and then we've covered it as well. So does that give us an induction proof? Well, nearly. We want the number of these orange dots to be a function of k. Okay? So in order for this to work, we need to find a cycle to start with. So we have some freedom here to choose a short cycle, for example, whose size is bounded in terms of k. And now, do you think such a cycle can be found? So how small a cycle C can we find in an arbitrary graph? Maybe, given that the arbitrary graph doesn't contain too many independent cycles, maybe not. Well, we can find a short cycle that has length at most, C at most T log order G. And this is how we do that. We just, well, there's one assumption we have to make. Just by making C big, we shall not be able to find a short cycle because C might be a cycle, right? So let's assume that the graph has min degree at least 3. That's not a big assumption, because if it doesn't, we can delete all the vertices of degree 1 or 0. We can suppress the vertices of degree 2 without changing the cycles very much, right? So we will never have to use a vertex of degree 2 in our hitting set, in the orange set, and suppressing it doesn't change the number of cycles or the set of independent, the sets of disjoint cycles either. So we can, without much loss of generality, assume that our graphs have min degree at least 3. Okay, so if that is the case, well, we can take a neighbor and find its neighbors, and then finding their neighbors, and so on. There's even one more here. And we can do that up to a height of, say, half the girth. And if we do that, then all these vertices that we're finding here are going to be distinct, right? If any two of them were the same, we'd have a shorter cycle, right? If this one was the same as that, we could walk down on a path of length half the girth, then up again to the same vertex here on a path less than half the girth, and we'd have a cycle shorter than the girth with a contradiction. So we can always find such a tree nicely spread out up to a level of about half the girth of the graph. And then how many vertices does that have? Well, it has 2 to the half girth vertices, roughly. And if we solve that for this g, this function g here, we shall get that bound up there. So there are at least this many vertices in a graph whose shortest cycle has length g, and therefore the length of the shortest cycle is bounded above by this value there, which is not good enough. Right? We want an upper bound in terms of k, independently of g. Now, maybe that isn't the best upper bound on the shortest cycle, the length of the shortest cycle. Maybe we can find shorter cycles in some other way. And the answer is not quite so easy, but the answer is still no, because it is possible in this construction here to join up all the leaves in such a way as to give each of them degree at least 3 without creating any short cycles, and that would show that this bound is essentially best possible. Maybe you have noticed that we haven't really used our assumption that we can't find k disjoint cycles in our graph. We've just said, well, given any graph G, how short a cycle can you find? And then that shortest length that we could guarantee wasn't quite short enough. But we haven't used our assumption that there aren't many disjoint cycles. So maybe if we find these edges here that give every leaf degree at least 3 without creating a shorter cycle, maybe the only way to do that is by making many of these cycles disjoint. Okay, so let's try a radically different approach. And that is, let's try to prove that just by making G large and assuming that the min degree is at least 3, maybe we can find many disjoint cycles. Might that be true? Just by making G large, well, if we can't find many disjoint cycles, for example, the graph might look like this, right? So many cycles here, but they're not disjoint. Well, but here are lots of vertices of degree 2 still, right? And if we want to somehow connect this graph, then so as to give them large degrees, at least 3, we might create a short cycle. And then there might be many of those. So just conceivably, it could be true that given k, if a graph is large enough, we might find k disjoint cycles. And large enough should be in terms of k, as a function of k. And if that succeeds, that proves our theorem. Why does it prove our theorem? Well, we could always choose f of k to be the largest size of a graph that doesn't contain k disjoint cycles. So if eventually, if the graph is big enough, we find k disjoint cycles, big enough in terms of k, then, well, if it's that big, we find the cycles. If it's one smaller, we can cover all the cycles by deleting all its vertices. Still a function of k. Okay, so that theoretically might be an idea. So here's that second approach. Let's try to find a function, let's call it little s, such that if G has at least S of k vertices, we can find k disjoint cycles. That's a false statement that you might get an exercise asking you to find a counterexample, but let's see what happens. We don't know yet that it's false. So how would we prove that? So the idea is the same as before. We delete a cycle. Then we have the rest. And now all we know is that G is big. Now the rest is going to be big. And if we can find k minus 1 disjoint cycles in there, so how big is the rest? It has size, as we shall assume, at least S of k minus 1, right? And we want this to be at least S of k big, and then we're hunting for a way of choosing S of k given S of k minus 1 so that we can find one more cycle such as this one. Okay. So by assumption, we'd have k minus 1 disjoint cycles here, simply because that left half is big enough. So how small can C be? Well, as we saw, C can be found to be at most 2 log order k large, and then we'd get this inequality that you see there. So let me write it up here as well. S of k minus what we have to take away, and that will be 2 log order g. That is what we have left here, so that should be at least S of k minus 1. Right, we're looking for a function little s that achieves that. Right, and then the rest here would be if the whole graph is big enough because it contains S of k vertices, then C is no bigger than that. Then the rest will contain at least that many vertices there, and we want that to be big enough to guarantee k minus 1 disjoint cycles, so we want that to be at least S of k minus 1. Right, so can you think of a function S of k that does that? satisfy this? How can we define S of k once we have S of k minus 1 already, so as to make this true? It's not hard. It's enough to make S of k twice as big as this. Right? Then this can be written as a sum of 2 copies of that, and one of these will easily accommodate that. So that seems easy. There's still one little snag. Right, are we done? If we have, e.g., let S of k be 2 to the k, then that holds for k big enough. And big enough is not very big. That seems right. Well, we forgot, or I ignored deliberately, maliciously, one little assumption that we're always making, and that is that the min degree of our graph is at least 3. Right? Without that, nothing like this works. So if we want to apply induction, then we have to ensure that this side here has min degree at least 3 as well. And we don't know that, because these vertices here, they might have degree at least 3 in G, but that might have that by virtue of sending edges to C. And once we delete C and the neighbors that such vertices have in C with it, then suddenly the degree of such a vertex might drop below 3. So that is a problem. Okay, so let me draw a new picture and let's see how we can address that problem. So here's our cycle C. There's G minus C. And now we might have some vertices of degree less than 3 in G minus C because they send their some edges to C, and deleting those makes their degrees drop below 3. So the only way that we can ever hope to apply the induction hypothesis to this half here is by doing what we did earlier when we assumed that we have min degree 3, and that is delete the vertices of degree 0 or 1 and suppress the vertices of degree 2. So by suppress, I mean replace this path of length 2 by just that edge. All right? So if we do that, then we're back in shape to apply the induction hypothesis to this modified G minus C, provided, of course, it's still big enough. So earlier we said, yes, it is still big enough by assumption if we choose this function little s right. because we know that C is smaller than that, if the whole graph has size that, and then we have this many vertices left here. Now we have fewer vertices left here. So how many fewer than S of k minus 1, or than this preliminary S of k minus 1, which we want to make our new S of k minus 1 to get the induction to work? Well, we're allowed to delete or suppress a bounded number of vertices, bounded in terms of k. And then we can adapt our function S, and then that works again. Right, so that's a good question. How often can this appear? Right, it would be nice if we could find this cycle C not only short, but maybe also so that there is only a bounded number of edges across between C and the rest. Right, if there's only a bounded number of edges across, that would help us maintain our induction assumption that the left half is big, because any vertex that we delete or suppress sends an edge across. Right? If there are few edges across, then we have deleted or suppressed only a few vertices. So we want that number, ideally of the edges across, to be bounded by a function of k. Okay, so is that going to be true? Well, we know that C is small by assumption, right? Bounded by a function of k. If the vertices of C each send only a bounded number of edges to the left, then that number is going to be small as well. Okay, so in order for that to be true, we would like the vertices on C to have not only degree at least 3 in G, but also at most something. Right, so we would like to bound the maximum degree of G as well from above now. Okay, and that takes us to our third idea, which is eventually going to work. And that is, well, let's be bold and not just work with some maximum degree bound, but let's go for 3 as well. So can we prove that if our graph is large enough and cubic, then we can find many disjoint cycles, just because it's so big, right? And if we want to find k disjoint cycles, a size order of this graph of at least some f of k should be enough to ensure that. Right? And then, well, the graphs we want to deal with are not going to be cubic. But the strategy would then be to either find a large cubic graph in our given graph G, so that inside that we can find our desired disjoint cycles, or if not, then we can cover all the cycles of G in G by some f of k many vertices somewhere. And that strategy is actually going to work now. So we're going to deal with two bounds, little s of k order for a cubic graph H should force k disjoint cycles in H. And then we shall find another function f of k for G such that any G that doesn't contain such a large such a large cubic graph of at least s of k vertices somewhere inside it has the property that we can cover all its cycles by f of k vertices, where this f may have the function s in its definition. That's going to be the strategy now. So here's that lemma about cubic graphs, and that's what we're going to prove next. Right, so given a cubic multigraph H with at least some s of k vertices, or sk vertices, can we find k disjoint cycles? And this is another example where the value of sk is going to be found in the process of what we're now going to do in order to try and prove some such statement. Right? So we're trying to find a proof that for some function sk, any cubic graph H of order at least that sk contains k disjoint cycles. We're going to find that function together with proving that this does indeed work for the right function. Okay, so here we go again. Let's start with our short cycle C. Again, so the order of C is at most 2 log the order of H. Now, this whole graph is H. And H is cubic. Right, let's start with such a cycle C, delete it, and see what we can do to the left half. In order to make the left half cubic again, we change this partition that we have here into the vertices of C and all the other vertices by moving such vertices across to the other side. And notice that when we do that, when we move such a vertex across, the size of this cut will go down. Right? This vertex contributed at least 3 edges to this cut, and after moving it, it will contribute none because it doesn't send any edges to the rest of h minus c. And likewise, a vertex that had degree only 2 in h minus c. No, sorry, we leave those. We move the edges, we move the vertices of degree 0 or 1 across. Right, so a vertex of degree only 1 in h minus c sends at least 2 edges across, and after moving it, it sends at most 1 edge across. So moving such vertices across the divide will reduce the cut, the size of the edges across. So that's a nice observation, which can trigger the attempt to say, oh, right, well, let's start with the smallest such cut, not necessarily just with the smallest cycle, or maybe a bit of both. And, well, if we want a bit of both, then let's start with the shortest cycle, one that has size of most that, and then just do this process algorithmically. Then when it stops, we take that bipartition and work with the graph that we have left here. Okay, so every step of moving a vertex across will reduce the number of edges in the cut by at least 1. And how many edges are there in the cut? So let's call that number m. M is the number of edges in original cut. Okay, so this number m is at most the order of C, the number of vertices in C. Why can there not be more edges in the original cut? Well, because every vertex on C has already 2 neighbors on C itself, and it has 3 neighbors altogether. So such a vertex here might have its 3rd neighbor also on C, in which case it does not send any edge across. Or if it doesn't, then it sends 1 edge across. Okay, so how many edges across can we have at the start? At most, as many as C has vertices, no more than that. And now we perform our reduction n times, n moves. And then after that, we have at most m minus n edges across in the cut, right, after n moves. Right, when we've done, then the min degree on the left is at least 2, by definition of done. right? If there was a vertex of smaller degree, 0 or 1, we'd move it. Okay, so the min degree is at least 2. And how many edges are there of degree? Only 2. Yeah? Nearly. At most, m minus n, right? At most as many as we have still in the cut, edges as we still have in the cut. N was the number of moves. And the number of edges in the cut dropped from m to m minus n, right? But that's what you meant. So every vertex of degree 2 here must send an edge across. So we can only have as many such vertices as there are edges across, which is m minus n at most. Okay, and so we suppress those. Right. So we have deleted, we have moved at most n vertices, but yeah, n we don't have a bound for n. But we don't need a bound for n because the rest now works already. Or maybe let me copy that to the board so that it's recorded as well. So we had the graph H that we started with, and the left-hand side originally had order H minus order C vertices. Then we moved n vertices across. So there were this many vertices left on the left. So new left side, at most this big, sorry, at least this big. Right, it was earlier at least this big, and then we moved n vertices across. So it's at least that big now. And now we've suppressed at most m minus 1 vertices, right? So we suppress at most that many. So how many do we have left in the graph that we're going to work with, the cubic graph that we obtained? Well, at least, and let me start, continue down here, at least order H minus. Let's combine this there and replace minus m, where is it, minus m by minus order C, which we can by this inequality. M is at most order C while maintaining this here. So we get order H minus 2 order C. And that is at least order H minus, well, we have a bound on C, so that's 4 log H, which now, by assumption, is at least Sk minus 4 log Sk. right? And that there's some monotonicity argument needed there, but that works for all k bigger than something 7.5. Okay, right. So the rest that we have has at least this many vertices. So we want this to be at least S of k minus 1. Right, but now we're back with this inequality that we had earlier, which is still here, except that this 2 has now metamorphosed into a 4. We want this to be bigger than S of k minus 1. And as before, we can easily achieve that, for example, by letting sk equal 2 to the k, and then it works for k from 7.5 onwards. Okay, so that's the lemma. And now, all we need to do is prove the big theorem. For f of k to be sk, the function that we got from our lemma, plus k minus 1. So not much bigger. Right, so we're going to prove now that in an arbitrary graph, given any k, we can either find k disjoint cycles, or we can find no more than that many vertices hitting all the cycles. All the cycles. Right, and that's going to be easy now. So let's start with H, maximal subgraph with degrees 2 or 3 in that subgraph, right? So H is a maximal subgraph whose degrees are either 2 or 3 degrees in that subgraph. And the vertices of degree 3 we're going to call U. U is the set of vertices of that subgraph that have degree 3 in that subgraph. And C, curly C, is the set of cycles in the rest. So maybe I'll write this up there. U is vertices of degree 3 in H. Curly C contains cycles that meet H in exactly one vertex and avoid U. That's the definition of courtesy, sorry. Okay, and now we give a name to the vertices in which they do hit H, and we call that set Z. Z is the set of vertices in which cycles from curly C meet H. Every such cycle meets H by definition of curly C in exactly one vertex, and the set of all those vertices is Z. Right? And now we pick for every Z, sorry, for every vertex in Z, one of the cycles whose incident in curly C, whose intersection vertex with H is that vertex in Z, and let C prime be the set of all those cycles in C. So, for every orange vertex, we pick one of those cycles here, only one, and we put that in curly C. Okay, and those cycles are disjoint, right? Why are they disjoint? Well, if two such blue cycles, or even, so if two such blue cycles had a common vertex, it wouldn't be the vertex that those cycles have in Z, because for every little vertex in Z, we chose only one blue cycle. So they would have to meet outside H. But if they meet outside H, we find an H path in G, which we could have added to H, increasing its size and maintaining its vertices, maintaining its property that all its degrees are 2 or 3. Why? Because the inner vertices of such an H path have degree 2, and the first and last vertex are going to have degree 3, because in H here they had degree 2. The ones that have degree 3 in H were in U, and the cycles in curly C avoided this U. So the cycles in C prime are disjoint. Okay, and now we look at all those components of H that avoid Z and are 2 regular. So 2 regular component is going to be a cycle. Right? Those that are not, don't have a vertex in U, and that don't contain an orange vertex either. The set of all those cycles that are components of H that avoid Z and avoid U is going to be curly D. Components of H avoiding U and Z. Okay, and now C prime union D is a set of disjoint cycles. Okay, so the cycles in curly C all meet Z. Those in curly D don't meet Z. And they can't otherwise meet, because for the cycles in curly C, the vertices in Z are their only vertices in H, and the cycles in curly D lie entirely in H. So that's another set of disjoint cycles. Okay, so how many are there? If there are at least k, we're done. Right? We wanted to find either k disjoint cycles in our graph G, k is given at the start, or hit all the cycles with at most f of k vertices, where f of k is defined like this. Okay, so we assume that curly C union curly D is at most k minus 1. Right. So let X be the union of Z plus one vertex from every cycle in D, plus one vertex from every cycle in D. Okay, so this X has exactly size at most k minus 1. Because Z has the same cardinality as C prime, and we added one vertex from every element of curly D. Right. Now we're in pretty good shape. What does X hit? Which cycles does X hit? Well, it certainly hits all the cycles, not only in C prime, but also in C, right? Because every cycle in C that is not in C prime shares a vertex from Z, and therefore also a vertex from X with some other cycle that is in C prime. So X hits all the cycles in C, and by definition, it also hits all the cycle components of H that don't have a vertex in Z, because we added one vertex from each of those and put them in X. Okay, so this X, this size of X at most k minus 1 is going to be this k minus 1 here, because we're going to show that all the other cycles can be hit by the set U, and U has size at most sk. Why does x union u hit all the cycles in G? If we have a cycle in G, any cycle in G, call it little c, if it is a subgraph of H, then either it hits U or it doesn't. If it hits U, then we're hitting it with our purported cover U union X. So let me write this up. Then done as U union X hits all the cycles in G. So why does it? Give yourself any cycle little c in G. If it is not hit by a vertex in U, then but is a subgraph of H, then it's one of those components, right? Then it is a component by itself because all its vertices have degree 2 or 3. Those of degree 3 are in U. If it doesn't have a vertex in U, it has all degrees 2 in H. So it's a component of H, and the question is, does it have a vertex in Z or not? If it does, then it's hit by X. And that's what we want to show. If it does not, then it's hit by X as well, because it's going to be one of those cycles in curly D. Okay, so X union U does hit, these are the cycles that are contained in H. And a cycle that isn't contained in H, well, that meets H in exactly one vertex. It can't be disjoint from H by the maximality of H, otherwise we could just add it to H. And it can't hit H in more than one vertex. We can't have this either, because then we'd have an H path in G, which we could have added to H as well. And so a given cycle either is a subgraph of H, in which case we have seen it's hit by X, or if it's not a subgraph of H, then it must hit H in exactly one vertex. And those cycles are the cycles in curly C by definition of curly C. And they are hit by Z, which is a subgraph, a subset of X. Yes, question?
Meaning these are not really interesting, but why can't we have a cycle that hits H with a vertex in U and also, so to speak, leaves?
That's fine. If a cycle that hits H in a vertex of U is going to be covered by U union X.
But those are cycles that hit H in more than one vertex.
Sorry?
Those are cycles that hit H in more than one vertex. They already
Those don't exist.
Why?
Because by the maximality of H. Ah, sorry. No. That is, yeah, okay. So we could, I see. Right. So a cycle that is allowed to hit U, in which case we say, okay, fine, done, we've hit it, but you're just asking whether such cycles exist. Yes, they can exist because such a cycle here cannot, an H path in that cycle cannot be added to H because it would inflate the degree of one vertex, namely the vertex in U that it contains, to a degree of bigger than 3, and that's not allowed in H. So that's not a contradiction to the maximality of H. Such cycles can in principle exist. Not in principle, they can exist, but they're covered by U. Other questions? Okay, so what remains to be shown is this, that U has at most sk vertices. Unless H contains k disjoint cycles, which of course we're happy with too. Right, but that's exactly the lemma that we had. Right, the lemma said that if we have a cubic graph, and we can obtain that from H by suppressing all the vertices of degree 2, then if that cubic graph has at least sk vertices, then we can find k disjoint cycles in it. So once more, we have our graph H, vertices of degrees 2 or 3. We suppress those vertices of degree 2. And those are the vertices not in U. Okay, and we want to show, well, either way, how many vertices are left in H after suppressing the vertices of degree 2? Well, those in U. It used to be in U. Either there are fewer than k vertices, sk vertices, in which case we're happy. Or there are more, in which case we couldn't find k disjoint cycles in this graph with the suppressed vertices, and then those expand to disjoint cycles in H itself, and we're also happy.